What's up, music nerds? Today we're getting into chapter 14 of Hermann Helmholtz on the sensations of tone. As usual, the link to the webbook I'm reading from is in the description. You can read the entire text of the book there and listen to all of the music that he's talking about. So let's get into it. Chapter 14, the tonality of homophonic music. We're going to start with the earliest form of music and try to pinpoint how and why the enormous mass of tone that exists in the world was ordered into melody. Helmholtz assumes that music is some sort of expression of or response to human feeling, which is motion. Anxious thoughts, depressive thoughts, joyful thoughts, they all have a certain sense of motion in our brains and in our bodies. So in music, we create that motion with intervals and rhythm. Melodic motion is change of pitch in time. Now, measuring rhythm is pretty simple. We just count the amount of time spent in sound and the amount of time spent in silence. But we first had to separate the vast existence of time into individual increments, hours, minutes, seconds, to make that possible. So to measure pitch, we need to do the same thing. We need to separate the vast existence of tone into measurable increments. We consequently find the most complete agreement among all nations that use music at all from the earliest to the latest times as to the separation of certain determinate degrees of tone from the possible mass of continuous graduations of sound, and these degrees form the scale in which the melody moves. But in selecting the particular degrees of pitch, deviations of national taste become immediately apparent. The number of scales used in different nations and at different times is by no means small. So let's look at some of these scales and try to explain the intervals chosen for it. So if we think back to our consonant intervals, those intervals that did not create any beats, the most consonant ones, the octave, the fifth, and the fourth, are present in all known musical scales, according to Helmholtz. The Greeks used these intervals to divide the octave into two tetrachords. So we have our first divisions within the octave. But the mode of filling up these gaps remains arbitrary, and different plans for doing so were adopted by the Greeks themselves at different periods, and others again by other nations. But the division of the scale into octaves and the octave into two analogous tetrachords occurs everywhere, almost without exception. So that's where Helmholtz is going to start, and he's going to try and fill out this scale using the natural relationship of tones. Not totally sure what that means, but let's find out. We shall consider musical tones to be related in the first degree, which have two identical partial tones, and related in the second degree when they are both related in the first degree to some third musical tone. So we're going to find tones related in the first degree using this chart. These are the ordinal numbers for all of the partial tones of our tonic note, which is C for this table. And down the side, we have the same. The intersection is the note for which both these partials coincide, which is also represented by the ratio of the ordinal numbers. 1 to 1 gets us a C, 1 to 2 gets us a C up an octave, 2 to 1, C down an octave. And we're sticking inside the bounds of an octave away from our tonic middle C note. So these are all the notes related to the first degree. If we put these notes in order of how large the ordinal numbers are, we get notes lying in the octave above the fundamental note C and related to the tonic C in the first degree, arranged in order of their relationship. And those below the octave. Now, we could, of course, continue this table on past the sixth partial, but the resulting notes would be closer and closer to our tonic, which brings us to the question of what is the smallest interval admissible in a scale? Well, in the period of homophonic music, it seems musicians avoided intervals smaller than a whole tone, and here are some examples. The North African five-string lyre, or kisar, would have been tuned like this. We have this scale when the ancient Greeks added a seventh string to the kithara. The old enharmonic scale. So now Helmholtz is going to sort of work in reverse. He's going to construct a 5-note scale and then search for its usages. If we avoid a semitone, these are all of the notes related in the first degree to the tonic C in the octave above. And below. To get 5 tones in our octave, we have to add some tones related in the second degree, which means they both are related in the first degree to some third common tone. So to fill in the gaps, we have the D, the fifth above the upper fifth G, and B flat, which is the fifth below the lower fifth F. And Helmholtz has found some examples of these scales used in a Chinese song after John Barrow. And this Scotch air for the descending scale with no second or sixth. Now, if you use both the D and the B flat, we get this scale, which he finds in probably an old bagpipe tune. And if we swap the fourth for a third with this E, we get a more major sounding mode. Found in many Scotch tunes, as well as this Chinese temple hymn. And finally, replacing the fifth for a minor sixth, which we almost, but don't quite hear, in Auld Robin Grey. And of course, you can play all of these songs by clicking on them at sensationsoftone.com, but I'm going to move on to the scales of 7 degrees. We already heard the Greek scale of 7 degrees consisting of a tetrachord and a trichord with our kithara. In the best times of Greece, song was usually accompanied by an 8-string lyre, tuned so as to embrace an octave of tones selected from the diatonic scale. These were the following. Now below, he has transposed these all to begin with a C so that we can hear more of the difference. And he's put the ancient Greek names on this side, Galerian's ecclesiastical names here, and some proposed new names. And of course, just click it to hear it. Helmholtz proceeds to derive these scales in the same way that he did with the pentatonic scales, starting with the notes related in the first degree, and continuing on from there. Now, you might notice in his calculations, when we see the ratios of the pitch numbers below the note, they are not always the same. For instance, this D here is 9/8, and this D down here is 10/9. And this is because they've been derived, so to speak, from different intervals. The same is true for the B flat of the 7th. Slightly different pitches. So Helmholtz is going to use this notation to make it clear exactly what intonation he's referring to. Pitches derived from perfect fourths and fifths are notated like this. Those derived from major and minor thirds are written with a 1 in the subscript, just like this. So a major triad would be written like this. Now, D1 is a comma lower than D with no subscript, and that is equivalent to about 1/10 of a whole tone. And every number higher in the subscript is an additional comma lower in pitch. So we are going to need these distinctions when we talk about Arabic and Persian musical systems, which we will do next time. If there was anything in this video that you want to read for yourself or listen to for yourself, go to sensationsoftone.com and subscribe to the channel so you don't miss my video on the second part of this chapter. I'll see you then. Bye!